Let us talk about this problem. We are given an array. We need to find majority element in it if it exists. What is a majority element? An element in an array is called majority if it appears more than n by 2 times in the array, where n is size of the array. So if you have an array of size 5, then the majority element should appear at least 3 times. And if you have an array of size 6, then the majority element should appear at least 4 times. Because 6 by 2 is 3 and it should be more than 3 times. Let's see now these examples. In these examples, we have an input array and our output is any of the indexes of the majority element. Right? So majority element in this example is 8. Right? Because 8 appears more than n by 2 times. So our output can be either the index 0 or index 8 or index 3 or index 4. Any of the indexes of this 8, right? 8 appears at index 0, it appears at index 3, then appears at index 4, right? So we can print either as 0 or 3 or 4, right? Let's see this example. In this example, there is no element that appears more than n by 2 times. 7 appears exactly n by 2 times, not more than n by 2 times, right? So our output is -1. Let's see this example. In this example, 50 appears more than n by 2 times. How many elements we have? 7. And 50 appears 4 times. So our output is any of the indexes of 50. It can be 3, 4, 5 or 6. Right? So we can return any of these 4 values. Now please pause this video and think of an approach to solve this problem. Let us talk about the naive solution first. The idea is to traverse through all the elements one by one. For every element, count how many times it appears in the array. And if this count is greater than n by 2, then simply return index of this element. And if you traversed the whole array and did not find any element whose count was more than n by 2, you return -1. That's the simple idea. So we run a loop for I equal to 0 to n minus 1. Inside this loop, we initialize the count as 1 because array I itself is a count for that element. And then we run a loop for j equal to I plus 1, j is smaller than n, j plus plus. If array I and array j are same, then we increment the count of array I, right? How many times array I element appeared. And if this count becomes more than n by 2 after this loop, then we return I. And if we come out of the loop, we did not find any array I whose count was more than n by 2, we return -1. Let's see the working of this naive solution. We have this array. Initially, our I is 0. We count how many times it appears. We initialize count as 1. Right? Now we run a loop from here and we see that count becomes 2. Right? So this 2 is not greater than n by 2. What is n by 2? N by 2 is 8 by 2, which is 4. So your count should be at least 5. Right? And here you are getting the count as 2. Now we come to I equal to 1, this element, and we count how many times it appears. It appears only once. Then we come to the next element and count how many times this element appears. This appears 5 times. 1, 2, 3, 4, 5. So we are going to fall into this if condition 4 times because count is initialized as 1 and then we are checking from j plus 1. So your count is going to become 5. And this 5 is actually more than n by 2. So you are going to return index of this element, which is 2. So you are going to get the output as 2 for this input array. And this naive solution works in big O of n square because there are 2 nested loops and overall time complexity is big O of n square. Now please pause this video and think of an approach that works in big O of n time. Let us talk about the efficient solution. It works in big O of n time and takes big O of 1 auxiliary space. This algorithm is popularly known as Moore's voting algorithm. It works in 2 phases. The first phase finds out a candidate, and the first phase guarantees that if there is a majority element in the array, then this candidate is going to be the majority element. The second phase checks whether the candidate found out by the first phase is actually a majority or not. The need of second phase is only there when you do not have a majority element in the array. If I modify the question and tell you that there's always going to be a majority element in the array, you just need to find it, then only one phase is required. Please note that this algorithm may not always give index of the first occurrence of the majority element. It may give you some middle occurrence, and we'll see in this example that it gives you some middle occurrence. Let's now see the working of this algorithm. Let's first take a look at the second phase because it's super simple and we are not going to discuss it again. So we have a first phase which has given us a result. The second phase is simply traversing through all the elements from first to last. And what it is doing, it's simply counting how many times this array result appears in this whole array. And if this count is smaller than or equal to n by 2, then it changes the result to -1 to indicate that there is no majority element in the array. Otherwise, it simply returns the result computed by the first phase. Let's now see the first phase. In the first phase, we decide the first element itself as a majority. We initialize its count as 1. Then we traverse through all the elements starting from the second element. And for every element, we check if it is same as current majority. If it is same, we increment the count. If it is different, we decrement the count. And if count becomes 0, we reset the count and we reset the majority. Right? We reset the result and count both. Let's now see the working of this with this example. So initially, our count is 1 and our result is 0, this element 8. Now we run a loop for I equal to 1 to n minus 1. When we are at I equal to 1, we see that it is same as current result, so we increment the count. When we are at I equal to 2, we see that it's different from the current result, so we decrement the count and make it 1. When we are at I equal to 3, we again see it's different from current result. Our current result is 0, which is this element. So we again decrement the count. And this time we see that count is 0, right? So we come inside this if condition. And what do? We reset the count as 1 and we change the result. We change the result from 0 to 3, right? Result is now 3. Now we come to I equal to 4 and we notice that it's same as current result. Current result is here. So we increment the count. When we come to I equal to 5, we notice that it's different. So we decrement the count. Now when we come to I equal to 6, we notice that it's same as the result. So we increment the count. So we finally have this index as a result, right? And you can notice that it's not the first occurrence, but it is the majority element index. So first phase is giving you an index of the majority element. Let's now talk about the time complexity of this algorithm. We have this loop that runs big O of n times, and then we have another loop that also runs in big O of n time. So overall time complexity is big O of n plus big O of n, which is big O of n. Let's do one more example run to understand the algorithm better. I've changed the example here. In this example, we initialize count as 1 and result as 0, as we do here in this first step. After that, we run a loop from second element, and inside this loop, we check the current element with current result. It's different from the current result, so we decrement the count. Count was 1, now we make it 0. And since the count becomes 0, we come here and we reset the count as 1 and we reset the result as 1. Result is reset as current index I. Now we come to I equal to 2 and we again notice it's different from current result. Current result is this element. So we again decrement the count and make it 0. And once you make it 0, again you have count equal to 1 reset and result equal to 2 because count becomes 0 after decremented it. When you come to I equal to 3, you compare it with the current result. Your current result is at index 2 and this element is different. So what are you going to do? You are going to decrement the count, and after you decremented the count, your count became 0. So you are going to reset the count and you are going to reset the result as current index 8. Current index 3, index of 8. Now we come to I equal to 4 and we notice that it is same as this result. So we increment the count. Now count is 2. So our finally result is this element, right? Index of this element, which is a majority element. So step 1 has given majority element. Now step 2 is simply going to count the occurrences of 8 and it's going to find out it occurs 3 times, which is more than 5 by 2 times. So it's going to declare this as a majority element. The second phase is basically not going to fall in here and simply going to return the result. Let us now talk about working of this algorithm. In this algorithm, we traverse from left to right. We maintain a count variable and we also maintain a majority. So if we show that by an index I, if an element X is considered as a majority, then this is the only majority element if majority exists. No other element is majority. If we show that by some arguments, then we understand the working of this algorithm. Let's now show this. Let's now argue this. Let's consider these two examples. In this example, when we traverse from left to right, what happens is some elements increment the count, some element decrement the count. So elements that decrement the count, they kind of cancel the votes of others, right? So this element initially incremented the count, right? And this element then decremented the count. This element then again incremented the count to 1, and then this element decremented the count. So these four elements cancelled the votes of each other. And finally, this turned out to be the winner and was suggested as a potential majority till this index, right? That's how this algorithm proceeds with this example. Let's now see this example. This element incremented the count, this incremented the count, this decremented the count, decremented the count. And basically this also changed the count to 1, but it at the same time decremented the count for 8. So I'm considering only elements which decremented the count, right? And then these two elements incremented the count. So this is how this algorithm processed in this example, and you had this element as a majority element. Now to show that this is the only element which is majority, this here and this 6 here in this examples, we just need to show that there is no other majority possible. And we show it by dividing these elements till this index I into two sets. The first set contains the elements that cancelled out each other. So 6, 8, 7, 6. These elements cancelled out each other. And the other set contains those elements that did not cancel out each other. They just contributed to current count, current majority. So 6 is the only element in this example. Let's see now this example. This 8, 8 and these 6, 6, they are in the set that cancelled out each other. And the other set contains the elements that contributed to our final count or final majority. So we've divided into two sets. The first set contains the elements which cancelled out each other. Now, if we claim this thing that this set does not contain any majority, then we are done with the proof. Then we can show that 6 is the only majority if there is a majority. Now, how do we show that this set does not contain any majority, or this set in this example does not contain any majority? It's easy to show. This set contains pairs of elements, and every pair is having different elements. So these sets can be divided this way. These sets contains elements this way, x1, x2, then probably x2, x1, and then x3, x1, something like this, right? So if you have n elements which are divided like this into pairs, and every pair has different element, this x1 is different from x2, this x2 is different from x1, x3 is different from x1, then no element can appear more than n by 2 times in this set, right? Because every element either appears on the left side or on the right side. So at most it can appear n by 2 times, but not more than that, which proves that there is no majority element in this set and no majority element in this set, which shows that if there is a majority element, this majority element has to be there, this, right, in this set. And this is what this algorithm is suggesting. So this is how this algorithm works.